So in environments where the noise is very high, if my receiver is able to accurately get my signal without any issue, I can say the receiver is going to be very, very good. So that minimum level, signal level which your receiver can detect with a very good quality is called as sensitivity. You are speaking in a train where the train is going to have lot of people who are also shouting and making noise. Even in that noisy environment, if you are able to clearly understand what the other person is speaking, that means your receiver is very good, or I can say the receiver is going to have very good sensitivity. So the sensitivity will relate to the minimum signal level which your receiver can accept with a good quality, with a decent quality. So in the presence of noise, all the signal will become noisy and will carry little information. So we are defining thus a parameter called sensitivity to grade receivers based on this performance. So we define there are certain parameters where the receiver should have that value. So only those receivers are considered to be very good. So SNR is one parameter which will clearly say whether the receiver is good to receive the signal or it is bad in presence of noise. So SNR, signal to noise ratio. SNR, ideal value of SNR is infinity. SNR is signal power by noise power. So signal power divided by noise power. So our ideal amplifier noise power is 0. So SNR value will be infinity. Ideal amplifiers have infinite SNR. But it is impossible to have ideal amplifiers. So practical amplifiers have SNR in the range 6 to 25 dB. Although this 625 dB range is very difficult to attain, we fix this as our threshold. So if an amplifier is going to have 6 to 25 dB of SNR, we say it is going to be a very good receiver. And we are defining one more parameter called noise figure, is the SNR input by SNR output of a system. So if the circuit, you measure the SNR at the input of the system, you measure the SNR at the output of the system. If there is a change, then that will be measured by the noise power. If the input SNR is going to match the output SNR, the system is not going to add any noise, then noise figure will be equal to unity. Same thing we have seen in noise factor also, right? So if the system is not going to add any noise, then the noise factor is going to be unity. If the system is going to add any noise, then SNR at the output will reduce, the noise factor will increase. Okay, so and input noise is given by P signal by PRS. PRS is the, anyways, you are going to use a voltage source, and voltage source will have a resistor. That resistor will have thermal noise. So that noise is given by PRS. So it is P signal by noise power. Noise power is P suffix RS. In actual application wise, where you will see the receiver is connected to the antenna. So in the receiver, first you have an antenna, and this antenna will be connected to your receiver amplifier. Okay, and this antenna is open, it is in free space, so it can pick up noise also. So if it picks up noise, it will go to the amplifier, and amplifier will start amplifying even the noise. The amplifier is not an intelligent device. It will amplify whatever is presented to it, right? So definitely if the antenna is going to be very sensitive to noise, it can pick up noise signals, then the amplifier will just amplify the noise, which will increase your noise figure. So if we cross multiply this equation, we can find what is the P signal. P signal equal to PRS into noise figure into SNR at the output of circuit.